Well, welcome everybody to tonight's STEM lecture series presentation. I'm Don Barry. I chair the physical sciences department here at Mesa College. And we're really pleased to have Dr. Dave Draper with us tonight to talk about, well, ultimately NASA's plans to return to the moon. And my understanding is that Dr. Draper is also going to fill us in on some of the latest research from the planet Mars. So Dr. Draper and I went to college together at Humboldt State University. When were we there, Dave? In like the 1670s? No, I think it was after that, maybe the mid-1980s.
When mastodons roamed the earth.
Yeah, there we go. But it really gives me great pleasure tonight to introduce our speaker, Dr. Dave Draper. Dr. Draper is NASA's Deputy Chief Scientist, and he has almost 30 years of experience studying the Earth, the Moon, as well as the other planets in our solar system. And of particular note, Dr. Draper is deeply involved in NASA's efforts to get back to the moon, with the goal of landing the first woman there. So that's pretty exciting. Dr. Draper graduated from Humboldt State University with a Bachelor of Science degree in geology, and went on to University of Oregon, where he earned his PhD in geological sciences. And before I turn things over to Dr. Draper, I'll just mention as well that he plays a really, really mean guitar. He's a very accomplished guitar player. So it's fun to go on field trips with Dr. Draper because he serenades everybody at night with his wonderful guitar playing. So, okay, well, let me pull up the PowerPoint presentation. And there we go. Okay, Dr. Draper, take it away.
All right, well, thank you so much for the very kind introduction. I promise I will not play guitar for y'all tonight. And you know, Don says this, of course, but he hasn't heard me play in 35 years, so you know, take that for what it's worth. But I am delighted to be here to talk with you all today. I wish I could be there in person, but of course, COVID-19 has other plans. So let's go ahead next, please. Here's just kind of a roadmap for where we're going to go. I have 4 main sections here, and after the main part of the talk, I'm then going to spend a few minutes just kind of talking about how I got into this business. I am the beneficiary of a very long string of lucky breaks, but you know, there's a lot to be said for being in the right place at the right time. So we'll talk about that toward the end. So I'm going to talk about what's going on with the latest from the surface of Mars with our Perseverance mission, and then for the meat of it, perfect. You can sit right there. No, back. There you go. Just sit right there for now. I don't know. Do you have it going forward automatically? Because we don't want that. We want to go when I say go.
Yeah, no, we're good. So yeah, it's not going to go automatically.
All right, great. If you would go back, please. I'm going to, in the meat of the talk, I'm going to, after we kind of give you the quick update on what's going on with Mars Perseverance, I'm going to spend some time talking about our new Artemis program. And this is what Professor Barry was telling you about when we were doing the introduction. This is our program to get astronauts back to the lunar surface. And in particular, we are going to land the first woman and the next man on the moon. Keep going forward. Okay, and then I'm going to tell you a bit about the science that we have learned from the history of lunar exploration thus far, both human and robotic. And that is going to set the stage for this sustained return to the lunar surface, where we are going to learn what we have to learn in order to go on and get humans on the surface of Mars eventually some years later. Next, please. So here in the first part, let's talk, before we get into some pictures and stuff from the Martian surface, let me give you just a bit of background. Perseverance, and here at NASA, we use the nickname Percy because, you know, it just sounds fun. It's the latest in the long series of spacecraft that have been sent to the Martian surface, both orbiters going around from above and doing remote sensing of the surface, and landers that actually make it to the surface, some of which are just landers that sit where they land, and then others that are rovers like we have now. I'm not going to read every one of these, but what you can see is there's been a fair amount of activity over the decades with multiple missions in each decade, with the exception of the 1980s. And the reason for that is that NASA's primary interest in those years was the space shuttle program. And so the biggest news before the current one was Mars Curiosity rover, which landed in 2012. And at the moment, we have a fair-sized fleet of spacecraft at the planet, a number of orbiters, several landers, and so we're really working hard to understand what's going on. Go ahead, next, please. And the main goals of this mission, the overarching goal of the mission, is to try to work out whether Mars was ever capable of harboring life. Was it ever habitable, as we call it? And in order to determine that, it is the first step in the campaign by which we will collect and return samples to Earth from the Martian surface. And as I'll illustrate as we go through the talk, there's absolutely nothing better than to have samples of the material from another world to understand how that world works. And not just have, we got back to the grid view. What happened there?
1 second.
There you go. Yeah, just go view. Yeah, there we go. From current slide. There we go. Thank you very much. Sample return is really the gold standard in trying to understand other worlds. And in particular, we need to know not just that the samples came from Mars, but where on the Martian surface they came from. At the moment, we have about, I don't know, I want to say about 60 or 70 Martian meteorites. We know that they came from Mars because of their geochemical fingerprints, but we don't know where they came from. They literally fell out of the sky. We have no idea where on the Martian surface they came from. And as Professor Berry will attest, geological context is crucial for understanding what those samples are telling us. And then the third thing we're going to see a little bit about today is the Ingenuity helicopter. This is a technology demonstration. This is not intended to make any measurements. It's just intended to take the very first step in seeing if we can ultimately conduct powered flight on the surfaces of other planets. And so, of course, because we nicknamed Perseverance Percy, we have also nicknamed Ingenuity Jenny. So we're going to talk about Percy and Jenny tonight. Next, please. Now, you see these brightly colored maps, globes to the right of the text, and the next slide will look just the same except different text. Go ahead, Don. And what you're looking at in these colorful images are color-coded maps of the surface reflecting the surface's topography. And I'm looking to see, okay, great, I can see people moving. So I still need that next slide. No, you skipped one. No, go back. Back to, there you go. Thank you. Thank you. Okay, this is the same images, but different text, and I've got a little highlight on the upper one of these diagrams. Okay, these globes show where the high and the low parts are on the Martian surface. The hot colors are high up, high mountains and stuff. The blue and purple and cool colors are low basins and low areas. And the little red circle there with the yellow star in it, that's where the landing site is for Mars Perseverance. A couple things I want you to notice before we go on. First, you can see there's a huge difference between the southern hemisphere of Mars and the northern hemisphere of Mars. Southern hemisphere, very rugged, very cratered, lots of high standing ground, whereas in the northern hemisphere, it's much, much lower, much, much smoother. Another thing Professor Berry will agree with me on is when we're doing geology in the field, one of the most important things to look at is contacts, where things come together, because those contacts of one kind of thing to another kind of thing really tell us a lot about what's going on. And so this mission is targeting that zone between those two terrains. So we're going to start zooming in now over the next few slides and take a look at the landing site. So next, please. Okay, here's a regular view of the Martian surface now. This is just regular colors, so you can't see as much detail because it's just it's not bringing out those highlights. The zone we're going to be landing in is a little place called Jezero Crater, and the white circle on the right-hand side shows the crater. You can see it's just one of many, many, many small craters all around the area, and that crater sits on the edge of a very large basin labeled there as Isidis Planitia. Next, please. And here it is again, Perseverance landing site. This is an unwrapped globe splashed onto a flat screen, and it shows where some of the other landers have been. Next, please. Okay, and here we go. Now we're back to that same color-coded thing. High ground in the bright colors, the hot colors, low ground in the cool colors. Here you see the Isidis Basin, or Planitia as we named it before. Jezero Crater indicated with the little line. So you see it's just one of a whole bunch of craters, and it's really close to that boundary between the high standing material and the low standing material. Next, please. Okay, we're zooming in closer. The white circle you see, or ellipse that you see there, This was calculated before the mission landed. This was the sort of general area they were going to target. This mission has something new on it that no lander on Mars has had before. It's a technology that we call terrain relative navigation. It sounds like science fiction because about 20 years ago it was. What happens is we have a ton of photographic documentation of this surface, as you've seen already, and we're going to see more of it. And we have computers on board the spacecraft that have all of these images loaded in. And as it was flying down, it was looking at the surface many times a second and comparing the images it was collecting to what it knew the surface to be like. And it was calculated, it was flying itself. It was finding, using the terrain, where the safe landing spot was. So once the spacecraft got down to a certain level, it was hands off, everything, you're gonna take it yourself and land where you can. It's an astonishing accomplishment that it works so well. And I'll just say, this landing has gone, it went almost flawlessly. There was like one or two things that didn't work perfectly, which is almost unheard of in this business. There's always something. We even have a cliche. We say, that's your glitch for the mission. Every mission has to have a glitch, you know, but this one was nearly perfect. So it's really remarkable. Next, please. Okay, now we're zooming in. Now this is another color-coded map, but the colors mean completely different things now. These colors are about which minerals are present in the rocks. I'm not going to go into that detail now, but what I want you to notice is look at this funny shaped thing in the middle of this image. It's as geologists, we look at this and we say, that sure looks like a river delta. And a river delta go ahead and go to the next one, please, Don. A river delta is a place, we have bunches of them on Earth, where a river is coming down slope, and as it comes downhill, it's got lots of energy, and it can bring things along. And if you've been to a river, you've seen this. This stuff can get washed down the river all the time. But once it gets down, off the slope and gets down to flat ground, it no longer has the energy to carry all that stuff with it. And all that material, that sediment, just drops out. And so you see these delta features formed at the mouths of a river. Next, please. And so this feature in Jezero crater leads us to believe that the crater itself was filled with some big body of water, like is shown in this artistic impression. Now, on this view, Jezero is up to the upper left. You can see there's a river coming into this crater, filling it with water, and then you see another river off to the right where the water is leaving. And Jezero crater, the landing site is just outside the mouth of that river coming into the crater from the upper right. Next, please. And we believe, but we believe that the delta formed because there was that lake. And now we're going to see the 3-minute montage video of the landing. So if you would please, Professor, launch that video in YouTube and share that so our folks can see it. This is just a compilation of, about a 20-minute sequence into the highlights. And if you haven't seen this, oh boy.
It's going to take me a second here, Dave. So just be patient here.
Problem. You go ahead and I'll just keep talking here.
Okay.
What you're going to see is this is again for the first time. This spacecraft had not just still image cameras on it, but high definition video. And they took video on the way down. They took video from the rover looking back up at the parachutes while it was floating down to the surface. They have video pointing down while the rocket motors were gently settling the rover down onto the Martian surface. It's really something. Okay, awesome. Here we go. And maximize that if you can too.
Right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Conflict indicates chute deploy.
The navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 100.
You're looking straight down now. There's the Martian surface as we float down.
9.5 kilometers above the surface.
And that heat shield, they just dropped it off and it's just falling away. That's the thing that was protecting it on the way through the atmosphere.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface of Mars.
On the right-hand side, those are our delta deposits on the right-hand side of this image now that we showed you in those three.
On the parachute, we are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
LVS valid.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation.
Priming. TBA is nominal.
We have priming of the landing engines.
So the computer just figured out where to land. That's what they said. Terrain relative navigation.
Velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
Rover is flying itself right now. It's flying itself.
Completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver. Sky crane maneuver has started, about 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
All right. Yeah, you know, I'll tell you what, in this business, it doesn't get any better than that. You know, and I have been on the other side of that coin where I've been watching team, you know, the mission team members up on stage talking through, here's what's going on, here's what's about to happen for missions that didn't work, for missions that crashed. We're talking about 20 years ago or so now. And oh my God, the pain those people felt when it didn't work. Okay, so you saw some of this. You saw some of this on the upper right. The cheering in the control room. We had the President of the United States checking it out from the White House. Next, please. The President actually called our acting administrator, Steve Jerzik, and then called the whole team about a week later. Now this is a breathtaking picture. Now look at the big picture first. You can see to the left. Those are our delta deposits. Just to get you oriented. Now that's the thing I've been showing you several times. And in the inset, what you see is this is an image photographed from one of our orbiters, the Mars Reconnaissance Orbiter, hundreds of miles above the surface. And they knew where to look, and they caught the thing with the parachute, bringing the rover down in real time, and they caught it in the act. So this is, I don't know, I lose words for how amazing this is. Thank you. Next, please. And so here we are. Here's a good high-res image of the landing site. There's our big delta deposit there in the upper left. The landing site was named after the great science fiction writer Octavia Butler. Hugo Nebula Award-winning writer, died a number of years ago. Next, please. Okay, so here's some of the first images from the ground. This one is highly distorted because it's a panorama. So you see all the rover looks all crazy, and you can see those the scour of the dust blown away by the rocket engines when it came down. Next, please. We're going to go through these real quick, and okay, this is a great piece. Here's an outcrop of rock just sitting there. You know, when we were at field camp, we'd go running over there and start taking measurements and so forth. It's just a little piece of the whole puzzle here. And what I want you to understand is the far distance background. That's not the Martian sky. That's not the red Martian sky. That's the wall of that big, huge chunk of delta deposits. They stand like a couple of kilometers high above that basin floor. It's a huge stack of stuff. So what you're looking at is a kind of a telephoto lens view across that little knob in the foreground, all the way to the stuff that we're going to go drive toward. Next, please. All right, here's a picture from the underside. This big old device hanging off the front of the rover is our robotic arm that is instrumented, has all kinds of gadgetry on there to take measurements and do analyses and ultimately to collect samples to be stored for later return in a later mission a number of years from now. And so that's the business end of the rover. Excuse me. And there's a really cool looking rock right next to it. So let's go to the next one, please. Just, you know, they happen to be sitting there while they're getting started. They said, well, here's a rock. Let's take a look. And it's kind of weird looking. It's got these holes in it. It's kind of green colored. You can see the Martian dust is collecting in the holes. It's been there a while. Boy, what is it made of? Well, I don't know if you can see it in this view, but if you look a little bit to the right of center, you might see faintly a little row of dots evenly spaced. Next, please. Let's zoom in on that. And what you see, can you see? I hope you can see those little dots now. There is one of the instruments on board Percy is something we call SuperCam. And what it does is it is literally a laser beam that shoots the target, the rock, many times a second. And it has a spectrometer that looks down that line of sight, and every time the laser hits, it generates a little tiny puff of vaporized rock. And the spectrometer can look through that cloud of vapor and read what the composition is. So this is a way to shoot laser beams at samples all around you and get a really good idea of what their compositions are without having to actually go over and drive to it, which takes time. Now, I know that burning question is, what sound does this make when a laser beam hits a rock on Mars? When I was at NASA Johnson Space Center, before I came to NASA headquarters, we had a laboratory where we simulated a lot of these instruments on the bench so that we knew exactly what was going on. So we had a simulation chamber for this instrument as it was being developed, where we have a box that had Mars atmosphere in it. It was the right temperature, it was the right atmosphere composition, and the right low atmospheric pressure, all the right things. And they would shoot this laser and they would take measurements and, you know, gather all the information they needed. And the sound that it makes, have you ever been to a restaurant where they have one of those things up? It's meant to get flies. It's got kind of a UV light and an electrified screen. Fly will come along, and when it hits that electrified screen, it just goes zzz. That's what it sounds like. Zzz, 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 zzz. Everybody wants it to be pew, pew, pew. I'm sorry to disappoint you, but it's zzz, zzz, zzz. Only NASA. You can't learn this stuff anywhere else but from NASA, folks. So don't try this at home. Next, please. I don't know if you can tell, but I love what I do. Okay, this is the Delta deposit again, and this green line you see snaking its way around. This is the sort of game plan for where we want to drive the rover. Now, it's not easy to see in this view, but the landing site itself is just off the bottom of this picture. And the material that you can see at the bottom of the picture is a little bit of high ground in between the landing site and where we want to start our run. So the first thing we're going to have to do is go around that high ground and then drive to pick up the beginning of that green line. That's probably going to take a few months because these guys don't go very fast. They only go, a few meters a second. They're not drag racers. Next, please. But that's the game plan, is try to drive all the way up that thing and learn. We're going to take analyses and samples, and there's so much more to come on this. Now, the last few slides on Mars, we're going to talk about the copter, and it looks like I am going to be going a little longer than 35 minutes. I hope you don't mind. That we're going to see just a quick sequence of images here of the helicopter drone being unlimbered from the belly of the rover. So if you would please, just go every 2 seconds, just hit advance, and we're going to see the thing unfolding, and the legs coming down, and it's hanging there, and then eventually it's just going to be sitting on the ground, and the rover drives away. And it's ready, it's sitting there, and it's ready for its first flight. One more, and then stop right there. Go back. Back one more time. Okay, very good, thank you. This is, here it is. It's sitting there at the spot where it's going to take off from. Oh, please go forward one more, because I need those words. There we go. Thank you. It has had a chance to charge up its solar batteries. You see that panel sitting right on top above the propellers. That's its solar panels. It has this just happened. All these things just happened a few days ago, and it has actually survived its first 2 Martian nights. It gets real cold on the Martian surface at night. The atmosphere is incredibly thin. There is an atmosphere, but If you were to step out into it, you would die immediately because you just explode. It's way low pressure. And because of that, the temperatures get incredibly low. So surviving the night is a really important thing. The first flight is no earlier than 4 days from now. That's when they think that they could be ready the soonest. It might be a few days later. They're not going to go until they know they're darn good and ready. And what the plan is, with one battery charge, the drone can probably get about 4 to 5 minutes of airtime. So they're just going to pick it up, try to fly it around, and set it down. And then they're going to do that again and again and again until it stops working. And they're going to learn whatever they can from that process. I want to emphasize, a technology demonstration that's when it's okay for something to go wrong. Nothing's riding on this except learning engineering stuff, which is really important. But it's not going to kill the mission if this thing doesn't work. And even if it doesn't work, we're going to learn a lot. No matter what, we're going to come out a winner on whatever Jenny ends up doing. Okay, thanks very much. Now we're going to move on from Mars, and to go ahead, please. We're going to now start talking a bit about the Artemis program. And before we do that, I'm going to give you a bit of background of what we know about the moon from our early history of exploration, what we've observed, and how it sets the stage. So next, please. I'll try to pick up the pace. Okay, this is just a video. If you wouldn't mind hitting that button there, sir. I'm not going to go through all these. Just shows as time goes by on the bottom what was going on. This is the Apollo era. We had landers kind of scoping things out. We had a few orbiters, and then we had the Apollo missions, where 12 men, they were all men, were able to land on the lunar surface. So in 6 different missions, walk around for, the first one was Apollo 11. That was just a few hours. By the time they got to Apollo 17, they had 3 full work days on the lunar surface, driving around in rovers and doing amazing science. Next, please. And then there you go. There we go. So here we go. This is Jack Schmitt. This is from Apollo 17. Jack is the only trained geologist to ever live and work on another world. I've had the very good fortune to get to know Jack pretty well over the years. He's still very active in lunar science, comes to all the meetings. He's 81 years old and he's still going strong. Next, please. Here's where all the landing sites were. You notice they're all on the near side. They're all on the side that faces Earth. The reason that these sites were chosen, of course, we had scientific reasons for going to each of these spots, but the big driver was engineering safety. You can see they're all at very low latitudes, not too far from the equator. We're not trying to push the envelope anywhere. We wanted it to be safe. But what we couldn't possibly have known then, but we know now, was this part of the moon is actually pretty weird geochemically. It's very unusual. When you compare it to the average moon around the rest of the world, it's really weird. And so we've got a bunch of samples of this stuff, and we've learned a ton. But we don't have like ordinary, normal, average moon that we know where it came from. And so we're not even close to done understanding everything we can learn from the moon. Next, please. I'm just going to very briefly go through some of the things that we have learned from the samples brought back from the moon. I've said this before, samples are the best. That's how we understand exactly what's going on. Because when you go to another world with a bunch of instruments, like we have Percy on Mars right now, you can only analyze what you brought, you can only use the tools you brought with you. And if you were to find something that, oh man, look at that, what is that thing? But we don't have the tools to make the measurement, well, you're out of luck. But if you have your samples here on Earth, you can build a laboratory. You put the laboratory, we put them in these things, you can see them in the lower right corner. We keep them in absolutely perfect, pristine condition for decades because we know that eventually new technology is going to come along to allow us to ask questions we can't even think of yet. And that has paid off again and again and again over the decades as new important discoveries continue to be made from the study of the lunar samples. Next, please. Trying to pick up the pace here just a little bit. This is another, go ahead and hit this, I'll talk through it. This is the second era of lunar exploration in the 90s, and you can see it's almost exclusively orbiters from a variety of countries, not just NASA. We have China, Japan, the European Space Agency. China now has landed on the lunar surface more than once. In fact, they just last year successfully returned samples from the moon robotically for the first time in 40 years. And China deserves all credit for that amazing accomplishment. And those samples are now being looked at over in Chinese labs. They're going to be allocated to to researchers both in that country and elsewhere around the world soon. We're going to learn a lot. Next, please. One more. Yeah, you don't need to play that again. There we go. Okay. Here's our moon. Here's our beloved moon. We have near side, far side. Just make sure everyone understands. We have the near side that's always facing us. We call it being tidally locked. And that face just faces us as we go around every month. The far side is very different looking from the near side. When we look up at the moon in the night sky, we see those dark and light areas. On the far side, it's almost all light stuff, only a few bits of dark material. The dark material is basaltic lava. It's lava flows that filled in impact basins. I'm going to show you some animations about what that looks like in just a couple minutes. But there is no dark side of the moon. I know Pink Floyd has a great album by that name, but the moon goes around the Earth goes around the sun. It just takes 1 month for the moon to spin around when it takes us 1 day, but the entire moon gets lit up. It's not like there's one side that's always dark. But there's a but, and I'll come back to that in just a couple minutes. Next. Okay, this is another way that we saw something like this from Mars. This is topography. Again, it shows the near side very different from the far side. A lot of high standing ground on the far side, not so much on the near side. Next, please. And this feature you see to the lower right is labeled SPA Basin. That stands for South Pole Aitken Basin. It's near the lunar South Pole. It is the largest impact basin in the solar system. Absolutely cataclysmic impact. We're going to see an animation of that in a minute or so too. Next. How are we doing on time? Okay, not so bad. Okay, and we've now had other measurements made in the years since Apollo, during the 90s and the 2000s and more recently. And it doesn't matter what these colors mean. Basically, we are able to at least estimate the compositions of some of the rocks around the lunar surface. And this is how we know that the area we landed in is so weird compared to the average, because we now have global data sets. They're not very high resolution, but they're good enough to tell us that the places we landed were very different chemically from the rest of the moon. Next, please. We also learned a lot about the impact history of the inner solar system. I could talk about this subject for days, but the important fact I want you to remember for tonight is, or tonight for me, not for you, is that the moon, because it's a very different geological machine than the Earth, it has a record of events that occurred 4.5 billion years ago, still preserved today in the form of all of these impact basins. Here on Earth, we have this wonderful thing called plate tectonics, and we have wind and soil and erosion and water that consumes and recycles rocks. And rocks, for geologists, rocks are the pages in the history book of time. Rocks are the things that allow geologists to go back and understand what is the history of this world? What is the history of this area? And so we have all the pages of the book of history of our own Earth from those first chapters have been ripped out. They're gone. We have no idea what happened there because we have no pages left. But on the moon, there is evidence of things that happened to the moon and to the Earth that we couldn't have known any other way. And I'm coming up to one of my big punchlines. Next, please. All right, here's another animation, but don't start it yet. Don't start it yet. I want to tell you what you're going to see. I want to talk about the poles of the moon. Remember a minute ago I said there's a but about the light, no dark side. It does turn out that because the moon, I don't know if you can see my fingers here, the moon's axis is basically vertical, whereas ours on Earth is tilted. And because of that, right around the poles of the moon, and because the craters have such high walls, there are places where the sun is only ever coming in horizontally. And that means there's deep places that are always in shadow. And when I say always, I mean always, from like the beginning of time, always. And because of that, anything frozen that gets into one of those places, because the sun never shines, it's cold. It's going to stay there. And what we now know is we know there's water ice in there. And for sending astronauts to the moon and staying there and being sustainable at exploring, we need a source of water that we don't have to bring with us from Earth. Water's heavy stuff, and every kilogram you launch off the surface of Earth costs you money. So anything you can use that's already there is incredibly enabling. Okay, so what we're going to do in this video is you're going to see the moon tip over, and we're going to zoom in on the South Pole. What I want you to notice is and you'll see the sun going around because we're going to be fixing our view on the moon, and the sun will be going around us. And what I want you to zoom in, as we zoom in, you're going to see craters right in the middle of the view that are always dark. The sun never shines. So please start the video. Okay, here we go. You see the sun going around. This is all sped up, of course. And now the moon's going to tip over. Now we're looking at the South Pole, and we're going to come zooming in. And what you'll see is dead center in the view is one crater that we have named Shackleton. And watch that crater because it stays dark. Dark, dark, dark. And did it stop? Oh, there we go. All right, so there's that crater right in the middle, and you can see as the sun goes around, it just always stays in the shade. And that's true of a bunch of places around the South Pole. Next, please. This diagram here on the left is a kind of a summary of the video information you just saw. The dark spots, I know this is trained on the South Pole. You see kind of like a bullseye crosshair. That's the South Pole. The little crater that's just down and to the right of the crosshair, that's Shackleton that we just looked at. Those dark areas, this basically shows about what % of the time is the sun shining. And so you see that, you know, in the edges of the diagram, it's very gray. That means about 50% of the time, like normal. Half the time it's dark, half the time it's light. But when you get to these craters, you see that goes all the way over to zero, that at no time is there any sunlight. And on the right-hand side, another color-coded diagram, this time it's temperature. The hot colors are warmer, the cold colors are colder. And what you see in these purple basins, these purple zones, these craters, these are the coldest temperatures we have ever measured anywhere. That's an incredible thing to understand. The cloud tops of Jupiter aren't this cold. The mountains of nitrogen on Pluto are not this cold. These craters are just like 10 or 15 degrees above absolute zero. At absolute zero, molecular motion stops. It's cold. So nothing that gets in there that is, you know, meltable is ever going to melt. So any ice that or volatile stuff that ever gets in there is trapped in these permanently shadowed regions, as we call them. Next, please. All right, this is just a quick summary. In fact, let's just skip this. That just says the same thing I just said. All right, so again, go ahead, keep going. Okay, so that's what we've learned from the moon, and now we're in the home stretch. The last couple sections are nowhere near as long. And I'm going to talk a little bit now about how the Earth-Moon system came to be, because this is one of the most important things we have learned from going to the moon. And I'll give you a preview of my punchline. We now know that our own world was once entirely liquid, a ball of molten rock. We could never have known that unless we had gone to the moon. Next, please. Okay, we're going to talk about this process of accretion. That's the word we use. This is an artist rendition of the early solar system where we think there are these bands of stuff. This is how the planets we accrete. So they glom together from big pieces, get bigger at the expense of smaller pieces. We see this actually happening on the bottom of the figure. These are telescopic images, deep space telescopic images of distant stars in our galaxy that show this sort of process happening, at least at the time that the light left that image or that location some light years ago. So we know this is a good model. Next, please. Now, what we think happened here in the formation of the Earth-Moon system is that in that time, the very, very early time of the solar system, when there were still big pieces floating around, we had what we call the proto-Earth, what is going to end up being the Earth. But there was another chunk of material that was about the size that Mars is today, about 1/3 the size of Earth, that cataclysmically collided with the proto-Earth. We call this the giant impact. Not very imaginative. And we have, people have modeled this process to show how it would form the moon from material made of that impactor and from the Earth together to form a ring around Earth that eventually coalesced to become our moon. In the next image, and don't go just yet, you're going to see this color-coded thing on the right-hand side in animation. It's a numerical model. It's a computer model. And again, the colors are about temperature. Cool colors are cold, yellows, reds are hot, Anything that is red is molten, completely liquid, nothing solid at all. So please, if you would, the next one. Oh, I'm sorry, I forgot this. Skip it. We don't need to know this. Okay, here we go. This is an animation. All right, boom. And you notice, look at that thing. It's just like a blob of water in floating in zero G. It's just completely liquid now. And all this material is flung out and it continues to rotate. And all this stuff that's on the outside, some of it's going to come back and hit the Earth again. We're going to see a big one happen in just a second. But the rest of it is going to end up collecting in a ring around this now molten blob of stuff. And that's going to come together and form its own molten blob of stuff. So in the end, you have Earth sitting there completely molten, and you have this blob of new molten material that was caused by the giant impact. Next, please. We're going to have like 3 of these animations in a row. Now, that was a numerical model. Here's an animation put together by the BBC. This is what it might have looked like. So here comes the impactor, 1/3 the size of Earth. And I'm telling you, friends, this is a bad day. You do not want to be here. So incredible amounts of energy, and it's enough to just melt everything. In fact, it vaporizes things, atomizes things. So we're just going to watch this run. This is the process I just described from the numerical model. Now it's being really sped up. So here's the moon, the little one, sucking up some of that stuff. And it's going to, eventually, be the moon. Now, it's much, much closer to Earth at this time. Much, much closer. And here's what it would look like if it were rising above the horizon. You're sitting here on the molten Earth, and it's really close, way closer than it is today. And over time, it has gotten further and further away. Okay, now what we're going to do, the next, when this one's about to stop, it's got one more scene, and then it'll stop. So here it is. Here's the 2 molten blobs dancing around each other. Okay, one more. And we're going to see now, we're going to pick up, keep going. We're going to pick up from where this one leaves off. All right, so now we're going to focus on the moon. And it's going to start out molten, like we just saw. So here it is. Totally liquid, and it's cooling off. Now this is really sped up, so it's cooling off way fast. So here we are, 4.5 billion years ago. And remember I told you about the South Pole Aitken Basin, the biggest in the solar system? Well, here it comes. 4.3 billion years ago, that's the South Pole Aitken impact, which caused, this amazing, this was almost enough to break the moon in half, but it wasn't quite. And that basin persists to today. And then as time passed, more and more impacts happen. Again, we're in the early part of the solar system, the first 700 million years or so, lots of stuff still floating around. We call this the late heavy bombardment. Late because it's late compared to the very beginning, not late compared to now. And lots and lots of these very large basins. I showed you a map of those basins a few minutes ago. After the basins were formed, it took a couple 100 million years, but eventually the moon's mantle melted and started to fill in those basins with the basalt, the dark stuff that we see when we look at the lunar surface from here at home. And here it is. It's finally cooling off. It's starting to look dark. We're not done yet. We still got about 1 billion years to go. It'll only take about 30 seconds. There's one last phase of impact history here. It's kind of the flotsam and jetsam, the leftovers after the big accretion is over with. And so there's still a few more coming in. And then there's going to be one last pulse of little stuff right, in geologically recent time. And very soon the moon here is going to start looking like we all know and love when we go out in the night sky and take a look at it. So we're just about done with the animation. Okay, so now you've seen the whole history of the Earth-Moon system in about 5 minutes. Not quite binge watching, but we're getting there. Okay, let's go ahead and keep going. How are we doing? Okay, yep. I'm in the home stretch now. Now, this is going to take me a minute to explain, but it's still something that's really amazing. You saw all those objects coming into the inner solar system and raining down on the moon. Of course, all of those were hitting the Earth too, by the way. It's only 250,000 miles away. But because we have erosion and all those things, we don't have any record of that at bombardment, but we do on the moon. Why did all that stuff come raining into the inner solar system at that particular time? Well, we think the answer is that the outer planets, the big giant gas planets in the outer solar system, changed their relative positions to one another. And in so doing, that changed the sort of gravitational budget of the outer solar system, and it made things that were stable before start moving around. And it really kind of flung all this stuff into the inner solar system. So here's some things we know. We know that our own Earth was 100% molten rock at some distant point in the past, in the very beginning. We know that the outer planets danced, changed where they were to where they are now, and in so doing, flung all this stuff into the inner solar system. There's no way we could have ever known these things unless we had gone to the moon, because all the pages of our history book are gone, remember? That's, you know, if anyone ever asks the very reasonable question, why do we go? What do we do this for? This is one of the reasons. I don't know about you, but for me, you know, the fact that the Earth was once completely liquid is kind of got to be one of the top 3 most important things that's ever happened to the planet. And this is why we go. We go to learn things. We go to learn things we couldn't have known before. We go to explore because it's human to explore. What's around that bend? What's over the top of that hill? What's down that river? Let's go find out. That's what it's all about. Next, please. Okay, next, please. I'm trying to pick up the pace. Yes, yes. The moon is the foundation of planetary science. Told us about the inner solar system and the outer solar system and about our own world. Next, please. All right, let's talk about Artemis. Next, please. What I'm going to show you here is some very notional stuff, but before we do that, I want just a couple of pieces of background. Artemis in the ancient Greek mythology was the sister of Apollo. So it's a very natural choice of a program name when we're going to land the first woman and the next man on the lunar surface. Artemis is different from Apollo in a lot of ways. Artemis is about partnerships. This is not just a NASA program. We now have a robust commercial space sector. We have international space agency partners. We have academic people. We have people in industry. There's a huge coalition that's doing this. And this is not just going back to plant a flag and walk around again. This is a return to the moon to stay. Next, please. So we're going to find a way to live and work and do science on the lunar surface for long enough and get good enough at it that we can move on and go on to Mars. Next, please. But still stay on the moon. It's time to go out. Now, I'm going to go through these next couple slides real quick. This is a sampling of some of the commercial partners we have who are building spacecraft right now. There's going to be some launched later this year to send robotic spacecraft, much smaller than what we have on Mars right now, but still pretty capable, to go to various spots on the moon to start preparing for the return of humans. Next. Here's another slide of some more commercial partners. You may have heard of SpaceX, for example. These are, no one has been chosen yet. All of this is still in competition. I'm not giving away any secrets by showing these slides. All this is public consumption stuff, but these can all change, but depending on who builds what, who gets selected to do what. So I'm saying all this on the recording so that you know that the plans I'm showing you here are just plans for the moment. We're working really hard to bring these plans to fruition, and things are changing still. We haven't settled on exactly how we're going to do things. So things I'm showing you today, they may be pretty different in a couple of months, and that's fine. That's just the way this stuff works. Next, please. So here we have a couple of these diagrams. We call these swoosh charts because of that big old thing going across. And this just kind of shows that as time goes from left to right, we're going to start our campaign on the moon with some of these commercially provided robotic assets. Next, please. Eventually, we're going to get to the first human landings, the first crewed missions again. We're going to have an orbiting platform to help us do this, to provide science support and habitats where people can live, both in orbit and on the lunar surface. And next, please, do this for long enough and have infrastructure on another planetary surface to figure out how to live and work, and then we can try to set our sights on the red planet and expand human presence into the solar system. Next, please. All right, let's go one more. Okay, so here I'm getting, now you know I'm getting to the end because it even says punchlines. So Artemis is really about building on those past advances that I told you about that we learned from Apollo, and it's about the partnerships and the coalitions. And this is a message, another message I want you to take away from my talk to you today. You know, it's when we think about space travel and space exploration, naturally, everyone focuses on the astronauts and the mission controllers and all that stuff. But I need to tell you, for every astronaut that goes to space, who puts on a spacesuit and launches, there's at least 10,000, probably closer to 20,000 people here on Earth that have to do a whole bunch of different things to make that possible. And it's not just the scientists and engineers and the technologists. We need you all. We need all of you who are listening to this right now, because we need people who do all the other things. We need HR folks. We need accountants. We need farmers to learn how to grow food. We need architects. We need people who can build roads. My goodness, we even need lawyers, okay? My point here is that your life is going to take a road. All of our lives go on a road. There's going to be a time when your road and NASA's road and the Artemis road is the same road. And when you see that opportunity to merge onto that road, I'm urging you to take that opportunity. There's going to be a lot of chances. There's so much to be done. There's so much we can help we need. I was born in 1960. I am the Apollo generation. You are the Artemis generation. And it's your turn to take those next giant leaps and lead us into the future. And we're going to help you do it. But I couldn't be more serious. We need you to come with us and help us do this. Next, please. Okay, so that's the technical formal part. And what I'm going to do now is I'm going to spend just a couple of minutes just kind of describing my road, how I got to be sitting here with a NASA meatball on my shirt, with the privilege of being able to describe to you the American, you pay my salary. I am your tax dollars at work. We try hard to do good for the country and for our fellow citizens. And when I say it's a privilege to tell you about this, I could not be more sincere. I wake up every day and realize I get to do this, and I am so lucky. Now, it didn't start this way. When Professor Barry mentioned as he introduced me that I've been a guitar player a long time. That's what I wanted to be when I grew up. I wanted to play guitar. I wanted to be a classical musician at first. Then I discovered rock and roll, and I decided I wanted to be a rock star. That didn't work out, but honestly, it's a really good thing it didn't work out, because being a musician is tough. And not very many people make it. What I get to do now is things like this and help all this happen. And every time I pick up one of my guitars, it's to have fun. It's never to go to work. But as a music major, I had to take a science course to, check a box for my music major. And I took a geology course. This was in 1980, and the volcano Mount St. Helens in the state of Washington was just getting ready to erupt at that time. And we were paying attention to it in our earth science class. And when that thing erupted, it absolutely blew my mind. It was, for those days, it was a huge media saturated thing. I mean, there was no internet and all that stuff back then, but it was just massive. And it absolutely changed my life for that to happen. And I thought, I made kind of an ill-informed decision. I didn't really understand fully that to do geology, you need to take math and physics and chemistry and all this other stuff. I was a music major. I didn't take any of that stuff when I was in high school. So I had a bit of a rude awakening when I first started. However, I managed to figure it out, and was lucky to go to Humboldt State University in Northern California, where Don and I met, and had a great education there and learned a lot. And what most importantly, I think, we had a bunch of folks there who really supported one another. There are places in academia where the students are out to get one another and knife each other in the back, claw their way to the top. There, not many, but there are some. We were not in that mode at all, and it was so healthy and so stimulating. I'm so glad I went there. And then from there, I went to graduate school in Oregon. I was really interested in volcanoes, of course, and Oregon is a volcanic wonderland, and I learned how to understand what was going on in the field. I did laboratory experiments. That was my main thing. And I was able to go from there to do a couple of what we call postdoctoral fellowships, one in England and one in Australia. I was able to come back and find a couple of not so great jobs, but in my field, technician kind of positions. And, I hung in there long enough to be eligible to compete when a job came along to go to NASA Johnson Space Center and run a laboratory there. Now, I wasn't a NASA employee as such. I was hired by NASA to do this work in a laboratory, but that was my way in. And I set about trying to make myself indispensable, as best I could. Learned a lot and managed to be able to achieve some things. And from there, I had another stint in academia at the University of New Mexico, But then from New Mexico, I was hired back to Johnson Space Center by NASA as an actual NASA employee, and I've been with NASA ever since. And while I was there, I was able to lead an office, research office, the Astro Materials Research Office at Johnson Space Center. We call samples of stuff from other worlds Astro Materials, where we do all this, really high resolution analysis of samples like the Apollo samples to understand how these other worlds are made. And then from there, I was very fortunate to be selected to be the next deputy chief scientist at NASA. And I came to headquarters in July of 2019. And just for a bit of background, NASA has a chief scientist, a chief technologist, a chief engineer, a chief medical officer, down the line. And those are not the same things as the parts of NASA that fly these missions. And I'll be honest with you, the mission directorates, I mean, that's where the money is. They're the ones who pay for the missions. That's where the mainline activity works. Our offices, on the other hand, are outside that. And as a consequence, we're viewed as very objective observers. We're not trying to protect our budget, for example, because we don't have one. But we advise the NASA administrator directly. We're part of the senior staff. And so all these chiefs have a deputy and a staff and so forth. So I am the deputy for the chief scientist. And it's a privilege to be in this role, something I dreamed about when I was a kid. When I was young, I ate, drank, slept, and breathed the Apollo program. But of course, by the time I got to be a young teenager, I was all about music and not about science. So who knows? But I guess my takeaway is here. Even a path like mine that started going in the completely different direction from ever ending up with the space program, you just never know where the bumpers on the pinball table are gonna take you. So I guess I'll close by saying, keep your mind open, recognize that there are going to be opportunities. And I'd be happy to keep in touch with Professor Barry and his whole department as we go forward here. There are internships, there are studentships, there are ways to if you're really interested in this, you can get a degree in planetary science, you can go on to grad school, but you don't have to, okay? Again, we need people from all walks of life, all backgrounds, all educational levels, and because what we're doing at NASA is for humanity. It's not for it is, we want to be proud of our country, but this is something, so I think all of us have seen this past year of the pandemic. Our world is going to be different. We're not going back to some pre-COVID things. And I think that's many of those things we don't want to go back to. We've seen some terrible things in this past year. We really believe that Artemis and the goal of giving humanity a new home, an additional home besides our Earth, is something that can help bring us all together, give us something we can all get behind, no matter our differences, a way of bridging the differences. And so I'll leave you with that, and thank you so much for your attention and the invitation to come talk to you today.
Well, thank you so much, Dr. Draper. Let's all give Dr. Draper at least a virtual hand. That was absolutely wonderful. I know there are people that probably have tons of questions. I know I do, but I'm going to defer to you all tonight. So what I'm going to do is enable the chat at this point, and then I'm going to encourage people to use the hand raise feature. And then what I'll do is I'll call on you if you raise your hand electronically. And then I'll unmute you, and you can ask your question to Dr. Draper directly.
Yeah, sorry I went so long.
No worries. So does anyone have any questions? Let's see. Oh, great. Zach, go ahead. Are you there, Zach?
Looks like he put a question in the chat. Why don't we do that? It says, and there's another one there too. Okay, I'm going to go in the order they were posted. There's one here that says, are there any internships at NASA for college students? There absolutely are. In fact, we just selected a couple of summer interns for our own Office of the Chief Scientist just yesterday for this coming summer session. I'll be happy to send to Professor Berry some links and information, but the short answer is go to interns.nasa.gov and you'll see links to all kinds of things. You can Google up NASA intern programs and they can get to it that way if you don't remember the link directly. There's a lot of possibilities, and not just with the agency itself, but we have university partners that also run internships. One in particular I want you to take note of is from the Lunar and Planetary Institute in Houston, Texas, LPI. LPI intern program has been going for some 35 years now. There are people who are high-level people at NASA who started out as LPI interns. It's one of the best internship programs out there, and I would highly recommend looking into that. The next question I see here from Zach, who was probably having a little, we had a little technical issues ourselves when we were trying to get this talk launched, so I can relate. What does my day-to-day look like? Well, that's a great question. I guess the short answer is I am a professional meeting goer. I pretty much go to meetings a lot. But when I'm at these meetings, I get to talk about, pretty much the high-level policy. But the day-to-day is we meet in the pandemic mode. All of our group, we come together every morning at 9:30 for half an hour. We just check in. We talk to one another. Hey, what you up to today? We have a social in fact, we have one this afternoon. Every other Wednesday, we get together for an hour at the end of the day, have a beverage, and just shoot the breeze and talk to one another. So we're really trying to maintain our connections that we had prior to the pandemic. But, most of the things I do is I'm speaking with other fairly senior folks in the agency. We're trying to set policies. Big part of what the Office of the Chief Scientist does is look out for the welfare of NASA scientists for their day-to-day lives. For example, make it easier for them to download journal articles from libraries so that they can use it to do their work. Make it easier for them to register to go to scientific conferences and things like that. We also are the holders of policy for the agency, things like scientific integrity. That's up to us to set those policies and issue the instructions to the mission directors and so forth for enforcing those. But it's not like we're big bad guys or anything. We all work very collaboratively together, and we develop these policies, in collaboration with all of our partners in our cohorts, colleagues, and try to come up with something coherent. Another big part of what I do is I interact with other government agencies. I sit on a number of subcommittees run by, get ready for some acronyms. I'm going to try to keep it down as best I can. But we have the Office of Science and Technology Policy, OSTP. This is commonly known as the White House Science Advisor's Office. So this is the office that directly advises the President of the United States on science issues. I'm not one of those people that talks to the President, but I'm on several of the subcommittees that OSTP runs to understand what's going on across the government, so that those people can talk to the President and know what's going on. One other thing that I spend a lot of time doing, and this, again, very lucky to do this, is we do get to advise the very top decision makers of the agency. In the pandemic mode with virtual backgrounds and all this stuff, I got to know these folks well enough. They were joking with me about what my virtual I had traded jokes with Jim Bridenstine, the former administrator of NASA. Dave, what's your background today? What is that? I was doing a Star Trek thing or something. And I'll tell you what, there was a lot of Star Trek nerds at NASA, a lot. Star Trek, Star Wars, all of that. It's I'm with my people. It's a lot of us were pretty nerdy when we were growing up, and so it's good to be among those people. So let me go to another one here.
Hey, Dave.
Dave,
Rob actually has a question. Go ahead, Rob.
Bring it in.
Thank you for meeting us tonight, Dr. Draper. Quick question though, what does a geoscience NASA internship look like? What are the requirements and responsibilities?
That's a great question, and it really depends on which program you go through. I'll focus on that one I was just talking about, the Lunar and Planetary Institute, LPI. There, if you're an undergraduate in a related field, doesn't have to be planetary science. It could be geology, chemistry, physics, astronomy, mathematics, engineering. You basically apply to the program, and the LPI internship works with the people at NASA Johnson Space Center. They're about 1.5 miles apart. When I was at NASA Johnson, I know everybody at LPI, work very closely with them. And what happens is the applications come in, and I'll tell you, it's very competitive. For every internship that is selected, there are probably 50 or 60 applicants. So it's a tough gig. But the people at Johnson will put in projects that they're interested in having an intern work on for that summer. So there'll be like a dozen projects there. And then the intern applicants when they come in, the people running those projects will go and look at all the application materials, excuse me, and say, okay, here are my top 4 that I would like to offer, because, you know, if I offer to the top one and somebody else offers that same person and they pick the other one, okay, I'll go down to my next one. So everybody kind of puts in a top 4. And then once that's all done, the people that get selected, there's usually one per, sometimes there's 2, but usually just one person is selected for each of those projects. And they try to be very thoughtful and intentional about whom they choose. Let's pick a student that has the right background to do this work. So, and that is going to be true in every program. No one is going to be thrown into something they have no idea about. It'll be something that is got some correlation with what you've been doing. And the intent of all of these things is to give you a real exposure to what it's like to do this kind of science. It's not about saying, I need a grunt to come in and count how many rocks I have in this bucket. That's, you know, we can automate that. It's about actually doing a science project. And so the challenge to the people putting the projects together is come up with something that can be done in 10 weeks time. That isn't just, you know, go sort these things out. And so that, you know, and that's a good process both for the intern and for the sponsor to learn how to focus their own thinking to, hey, here's a good project we can get done in 10 weeks. And there have been some great things that have come out of that. I hope that answers your question.
Looks like we have some more in the chat.
Okay, let's see here. Externships for community college faculty. Good one. I'm less familiar with this, but I know they exist. Now it's been a number of years, but when I was at Johnson, actually my first time I was at Johnson before I came back as a civil servant, we had actually a summer group of both they were both secondary education, community college, and like non-university colleges, you know, not big schools, but the smaller schools, who sent their faculty, faculty members to Johnson Space Center, and they stayed for about 2 months, and they would move, you know, they spend like a week and a half with this group, and then they go spend 2 weeks with that group, and then a week with this group, in order to just expose them to a whole wide range of things that NASA was doing, so they could then go back to their classrooms and convey all that, you know. And the reason I remember this so well is one year when one of these groups was on site at Johnson Space Center, I got to go along when that group was brought into the old Apollo era mission control room, the very one, and we watched a screening of the movie Apollo 13 on the screen. And, you know, we're seeing these scenes and we're looking at it like, hey, I'm sitting right where that's happening. You know, that was pretty amazing. So yeah, there are such things. I wish I knew more about it, but they definitely are. And again, I'm making some notes here about things I can send along after tonight and hopefully follow up on some of this stuff. Okay, I see another one next. What would happen if an astronaut stepped foot on the surface of Mars? Is it possible? Oh, heck yes, it's absolutely possible. They'd have to have a good spacesuit, just like on the moon, because even though there is atmosphere there, it's extremely thin, and you've got to have that protection. But it would be pretty much like walking around. Mars is about 1/3 the size of Earth. The moon is about 1/6 the size of Earth. So if you've seen any of the old footage of the Apollo astronauts, you know, bounding along, it's because they weigh a lot less on the moon. On Mars, that's still true, but not quite as less. You weigh 1/3 what you would on Earth instead of 1/6, but it still would feel very nice and easy and light moving around. We already know from having all the robotic spacecraft there, the ground is very solid. We're going to have to drill into the rocks to get them up and put them in our carrying case. So you'd have no trouble walking around there at all. Okay, let's see what we have here. What languages would be best to learn for planetary science? Worth learning Russian, Chinese, Japanese? That's an excellent question. I would say, oh boy, yes, learning other languages is very important. Right now, of course, we are partners with Russia in the International Space Station efforts, and there are a fairly large number of folks in the astronaut corps who have learned Russian. Japanese, excellent choice because we're really good partners with the Japanese space agency JAXA. There are several Japanese astronauts, and there's lots of folks that have been guest scientists on Japanese missions and vice versa. So Japanese and Russian would be excellent. I'll just have to say that right now, NASA, there's a law on the books that prevents NASA from conducting any kind of collaboration with the People's Republic of China. And I got to be very specific here, in bilateral relations. Bilateral means just the United States and China. If there's other countries involved, it's multilateral, and that's okay. That's allowed. But there are no bilateral collaborations between NASA and the People's Republic are expressly forbidden by law. So I have nothing to say about whether it'd be a good idea to learn Chinese. Let's see here. Next, how long do you think it's going to take us to be able to have sustainable life on Mars? Boy, that's a great question. I just don't know. It all depends on how long it takes us to figure out what we need to learn on the lunar surface and decide, when we're going to go to Mars. It's a long way away. It takes 6 months to get there. And once you get there, you've got to wait a long while before you can turn around and come home. It's not like being on the moon, where you can turn around, come home anytime you want. And it's only a few days away. If something goes south, you can, you got a shot. If something goes bad on Mars, I know the Martian movie and all that, but you're not coming home. So I just don't know the answer to that. It's going to be years. It's going to be a number of years. I think earliest 2030s, something like that. That, again, wild guess at this point. No one really knows. What was the composition of the green rock on Mars? Chemist in suspense. I know, me too. The data right now are being analyzed. So what I'll geek out a little bit here. When you shoot the laser at the rock and you measure what's in that puff of stuff, what you get are raw ones and zeros. Those are raw data that have to be reduced and converted into numbers that we can make sense of. But the first thing that has to happen is all that information has to be beamed back to Earth, and that takes time because we have to relay information from the rover up to an orbiter. We have to wait for the planets to align so that our dishes here on Earth are ready to lock on and send it back. They're not very high data rates. I mean, this technology, even though this is today's mission, all this stuff was built 6, 7, 8 years ago. It's not the fastest. So it's going to take some time. I would guess within a week or two, they'll probably have some preliminary results from those little zap pits. I can't wait. I cannot wait to find out what that is. Let's see, internships at NASA related to health. Absolutely. The Human Exploration Operations Mission Directorate, that's basically the whole human spaceflight world. They have a whole set of programs of their own. My world is in the science side. I'm nowhere near as familiar with the human exploration side, but I've got some familiarity. And I do know that there are a number of them. I don't know in detail what they are, but that site I mentioned before, interns.nasa.gov, will link to all of those, not just the science, but it'll link to everything across the agency. And then let's see, Zach has another one. Do you know of many material scientists and engineers that work directly for NASA? Oh yeah, lots. If so, what kind of work do they do there? If not, okay, there's no if not, there are. Okay, yes. Oh my goodness, yes. Advanced materials is a big deal at NASA. We have an entire space technology mission directorate whose purpose is to develop these new materials and adapt them for use in space flight and actually aeronautics as well, high-tech airplanes. And so there are so many things, developing lightweight materials that can withstand high temperatures, materials that can conduct heat in a certain way, a thermal insulation. Oh man, it's just endless. So lots and lots to do at NASA for someone in material science. We have another one here. Do you think the Space Force and NASA will work together at some point? I am not going to comment on the Space Force. Space Force is not NASA. It's part of the Department of Defense. We are completely separate agencies. That's all I'm going to say about that. I think I've exhausted what's in the chat box.
All right, anyone. Well, here's your last opportunity to ask some questions. Any final questions for Dr. Draper before we wrap things up? Okay. Well, gosh, thank you so much. Wait. Oh,
Rob just put his hand up again. He's got his hand up. Let's go one more time. Go ahead, Rob.
Go ahead, Rob.
Dr. Draper, I've done a little bit of research and reading on nano carpentry and how it was pertaining to materials on Mars. I didn't see a whole lot of what their findings were. Do you happen to know what any of that was for some of the elements?
Rob, you have stumped me. You have stumped me. I have to confess to you, I have never heard the term nanocarpentry before. Okay. So I'm afraid I'm going to have to give you a big goose egg on that one. Boy, that's a terrible way to end. I don't know, but I'm going to be honest. You know, I'm not going to make something up for you. But I do know, however, one thing I can tell you is that NASA has been a real pioneer all its history in the whole world of miniaturization. You know, when in order, because as I said at some point during the talk, mass is money. Everything, every pound and kilogram you launch off the surface of Earth costs money. So everything you can make smaller and lighter is to be desired. And you know, the fact that we all walk around now with all the world's knowledge a fingertip away is due to the kinds of work that not just NASA, but also the Defense Department in this country and other countries have done to try to make things as small and lightweight as possible. And we're all the beneficiaries of that. Good question.
Looks like Zach has a question. Go ahead, Zach.
Yeah, hi. Is this working? Is my mic working now?
Yeah, we can hear you fine.
Perfect. So I know that getting into NASA is a pretty competitive field. And I was wondering if you knew of any steps we can take now in these early stages, being at community college, kind of learning our prerequisites and all that stuff. Is there anything we can do now specifically that would give us a competitive edge to work for NASA or to do any sort of space-related work?
May I ask you a question, Zach? What is your interest in as a major, as a field of study? Have you just and I don't know yet is a perfectly good answer. We might have lost him there. Okay, let me go ahead and try to answer. The best thing to do is
hey, sorry, I was muted. My interest is primarily in material science. And everything that you mentioned about advanced materials is pretty much exactly what I would like to study and get into.
All right, then I would just tell you, keep doing that. You know, and I hate to, you know, I really don't want to come across as like you have to go to only the best 5 or 6 schools. That's absolutely not true. But for certain things, it really does help to go someplace that has a really solid reputation for that kind of work. Now, that's a little bit outside my normal bailiwick, so I don't really know exactly which those are. But I would urge you to. This is advice I got when I was an undergrad at Humboldt. In our last year, we had a visiting lecturer from Caltech, professor named David Stevenson, who's a very eminent planetary scientist, big thinker. Excuse me. And he gave a talk, and I went along with the faculty member, a guy named Don Garlick, who had been hosting the visit. We went out to dinner after his presentation. I came along. And I asked kind of the same question you just asked me to him. And I said, you know, how does one get into doing planetary science? And he just looked at me. He just looked at me and said, go where they do planetary science. Mm-hmm. And so I'm going to be a little more forthcoming and said, but it is important to you know, go someplace where there's a real bona fide program. If you go someplace where you may have one material scientist in a department full of engineers that concentrate on other things, you're not going to have a community to draw on. You're not going to have as good a working group. And one of the things that in my experience has been most important in being successful, not for myself personally, but just success writ large, is collaboration. No one can do anything just by themselves. Learning how to identify a good teammate, how to identify someone who'd be a good advisor. You need to ask questions. You know, that'd be a good piece of. Don't be shy about asking direct questions. What do you think about this? What are my chances to do that? You know, can you bring this furnace to 1600, or will it only go to 1400? You know, be direct. The thing that, excuse me, a lot of us fall into is like we want to like not say too much, maybe use a euphemism. You know, in this business, it's really better to just, you know, be forthcoming, straight about what you're after. If you don't tell the people with whom you're working what your goals are, they're not going to be able to help you realize them. So that would be a good lesson, is just be really good in your communication while you are going to some of these places that have a good, well-qualified program, and work hard. Work ethic is really important.
Okay, thank you so much.
Good question.
Very good. How are we doing, everyone? Anyone else? Going once. Going twice.
Good question. Good
Well,
questions.
Yeah, great
Hey,
I
question.
appreciate
Dave.
it.
Oh, Hannah wants to ask a question. Go ahead, Hannah.
All right, you get the last one. Hopefully I can give you a good answer this time.
Okay,
Go ahead.
how has NASA used any extraterrestrial technologies in their studies?
I'm sorry, I didn't quite catch the question. Could you say that one more time for me, Hannah?
Yes, has NASA used any extraterrestrial technologies in their studies or just in general?
To my knowledge, there is no such thing as extraterrestrial technology. The only technology we know of is the technology we have built ourselves. We know of no extraterrestrial capability of constructing technology. Am I missing your question? I feel like I'm missing.
No, you got it.
Okay, yeah.
We just see it. I see it on TV, so I was really curious.
Well, I'll tell you this. This is actually a great way to wind up. I absolutely believe there's other life out there. Absolutely believe it. The universe is so vast, so vast. There are so many planets, so many galaxies. It is literally incomprehensible how vast our cosmos is. And for that reason, I think there's no way that we're it. There's no way that we're it. I can't believe that. However, I also know, just from doing the math, Earth has been sending out radio signals and TV and stuff at the speed of light since about the 1920s. And when you calculate how far those signals could possibly have reached, there's only like about 30 stars in that bubble. It's got a long way to go before it can get out far enough for those other civilizations to notice us. Okay. So the odds of there being such a civilization in the bubble of space our radio transmissions have thus far encompassed, minuscule, absolutely minuscule. I don't believe there are such a thing as UFOs. I don't know what people are seeing. Maybe it's government stuff. I don't know. But I don't think we've been visited by extraterrestrials. Does not mean I believe there are none. I do believe there are some, but I just don't think we've met them yet. It'd be great if we did. And I hope they're not the Independence Day type. I hope they're more the kind of ET type.
Very
All
good.
right, I think that's a good way to end. That's a much bigger, much bigger than I don't know.
I think so. Well, again, thanks so much, Dave. Dr. Draper, thanks for your time. And I appreciate everybody being here tonight. We had over 50 people here tonight, and you all asked great questions. So one last time, I'm going to put the link to the master schedule in the chat. There it is. And like I say, within a day or two, once the Zoom recording becomes available, I'll post it on the link for tonight's talk. So that's where you can find it. So once again, thank you for being here, and thank you, Dr. Draper.
Thank you, everyone. It's been great. Great talking. I hope to see you in person next year.
Yeah. It was a great night. Okay.
Bye, everybody.
Take care, everyone.
Stay safe.
Bye-bye.